In this session, we will see how to write a Verilog code and the test bench for the parallel adder. In particular, it's a 3-bit parallel adder. First, we will see a full adder, the block representation of a 1-bit full adder. It contains the inputs. Let us define it as A, B, C, and the output, which is sum and Cout. According to the functionality of the full adder, we will write the expression for the sum, which is A XOR B XOR Cn, and for the Cout, which is AB plus BCn plus ACn. So this is the expression for the sum and the carry out or the Cout. So by using the full adder, we would be defining the parallel adder, and it is a 3-bit parallel adder, and we do have the combinations of full adder. That would mean that we do have 3 blocks of the full adder, and these 3 blocks of the full adder is connected with respect to each other through a wire where a simultaneous data operation takes place. We would see the block representation of the full adder. Again, what we have told is we do have 3 blocks which contains 1 bit of full adder operation. We will provide the inputs. Let us define the inputs as x0, y0, x1, y1, x2, y2 with respect to the sum, which is S0, S1, S2, and we do have carry in, which is C1, and the output, which is the Cout of the first full adder, is connected to the input of the second full adder. Let us define this as C0, and the output of the second full adder is connected to the input of the third full adder. Let us define this as C1, and what we do have the output, which is Cout. So this is the block representation of a 3-bit full adder, and we will write a Verilog code to this particular 3-bit full adder, and we have told that in Verilog we do have a different description style, and we will be defining the particular operation or writing a Verilog code in the data flow or description style, and a predefined word which is used in the data flow description style is the assignment statements. A Verilog code. So we will start with the module followed by the module name, which is we have defined it as PD. Next we will define the ports list, which is X, Y, CN, sum and CO. So this is the ports list, and we do have the ports declaration, and you can see we are defining 3 inputs with respect to the X and Y, and we can define this with respect to the vector representation. Input 2:0, that is 0, 1, 2 with respect to the variable X and Y, and also we do have the input which is Cn, which is a single bit, and we do have the output as again a 3-bit representation, which is sum, and we do have the output which is C out, and there is a connection between the first full adder to the second full adder, that is in specifically the output of the first full adder is connected to the input of the second full adder, and the signal is moving with respect to the output of the first to the second full adder, and we are defining with a predefined word which is called as wire, C0 and C1, C0 and C1. Next we will define the sum for the full adders, and next the carry out of the particular full adder using the expression that what we have defined of the full adder, which is for the sum and the carry out. So we are using an assignment statement, a predefined word which is an assign, sum. So this is the sum, what we are calling it as S0. What we have told is here it is A XOR B XOR Cn, and according to this what we do have X0 XORed with Y0 XORed with Cn, X0 XORed with Y0 XORed with Cn. Next we will use an assign statement for the sum S1, X1 XORed with Y1 and XORed with C0, X1 XORed with Y1 XORed with C0, assign sum S2, sum S2, X2 XORed with Y2 XORed with C1, X2 XORed with Y2 XORed with C1. So this is for the sum what we have defined, and we will see with respect to the carry out. We will use an assignment statement again, sum, a carry out what we have defined is C0, it is C0, and what we have told, it is the combination of the variables with respect to the inputs, and here what we do have, again we do have the combination, but in terms of the operators of Verilog, the and OR are replaced. For the C naught, what we do have, it is X naught and Y naught, which is ORed with X naught and Cn, as you can just see, X naught and Cn, which is ORed with Y naught and Cn. So this is the first expression in terms of the carryout of C naught. Next, what we do have for the second full adder, assign C1. So assign C1, what we do have, it is X1 and Y1 ORed with X1 and C naught ORed with Y1 and C naught. So this is the second expression with respect to the output of C1, and the last what we do have is C out. Assign C out, which is X2 and Y2 or X2 ANDed with C1 ORed with Y2 and ANDed with C1. So we have defined for the sum and we have defined for the carry, and the last what we do have, we have started with the module, and next what we need to define, it is the end module. So this is the Verilog code for a 3-bit parallel adder. With respect to the particular block, we have converted into the program. To see the functionality of this particular Verilog code, we need to write a test bench by providing the set of in. Write a test bench for the parallel adder. Again, it starts with module followed by the name, which is PD underscore test bench, it is TB, and we have defined the inputs and the outputs with the registers and wires in the test bench. Register, a 3-bit of the operation with a variable x and y. Register, it is C in, wire, again a 3-bit of the operation, which is sum, and the wire, which is C out. So we will interlink the inputs and the outputs of the Verilog code with the test bench, which is PD unit under test. So we do have the inputs, which is X, Y, Cn, sum, and C out. So we will start with initial begin and we will provide the inputs. Let us define X as with a particular value, which is a 3-bit. We are designing for a 3-bit parallel ladder, so we need to define the values with a 3-bit. So it is a 3-bit, and the assigned value, let us say the assigned value is 0 0 0 for x, variable x, and next what we do have y, which is a 3-bit, and the assigned value is 1 1 1, and we will define C in, carry in, as a single bit of representation, which is 0. Suppose if you just simulate this, then the output would be an addition of these x and y of 3 bits, where you do get the output in terms of sum and in terms of the carry out. Again, we will define the timing scale as 10 nanoseconds, and we will write the another inputs. Let us say it is 101, for the y, variable y, it is 001. So we can write n number of inputs as we have told in the previous sessions. According to the inputs, what we do get the simulated outputs. Zero 1 0, 101 for the 10 nanoseconds, it is 110 001. So we have initiated with initial begin, we will end, and we have started with the module, and what we do have the particular end module. So this is the Verilog code and the test bench for a 3-bit parallel ladder, where we do have simultaneous addition that takes place. We are using the 3 blocks of full ladder to define a 3-bit parallel ladder. Thank you.